Hello and welcome to the first video in this Foundations of C course. In this video we're going to discuss some fundamental topics and get an environment set up for future development. But first of all we're going to have a quick crash course in computer architecture because it doesn't make too much sense to talk about computer programming if you don't really know how a computer functions on the inside. So here's an abstract diagram of a computer, and if we take a look inside we'll see that actually most computers consist of one or more CPUs, some form of memory, and some other stuff which we're not going to discuss right now. The CPUs or processors actually perform the computation, for example addition and subtraction, and store their results and other data in memory. Now in this course we're typically going to be talking about uniprocessor architectures, so that's computers with a single CPU, and instead of talking abstractly about memory, we're usually going to be talking about RAM, which is a specific type of memory. Now I said CPUs perform computation, but let's look at that in a little more detail. If we go up close to the CPU and take a look inside, we'll see that actually most CPUs, at least in the abstract, consist of a control unit, which is really the heart of the processor directing its operation, and some registers, which are just sections of really fast memory within the CPU, within the processor. Broadly speaking, the processor has a certain set of instructions which it understands. For example, an instruction to add two numbers together. And the control unit manages the execution of these instructions, commonly storing the results in registers. Once results are stored in registers, the CPU can then push these values to other places if required, such as to RAM or to the monitor. Using these ideas, we can begin to construct the concept of a program, which is really just a series of steps to be performed. Typically when we talk about programs, we're really just talking about a series of instructions which live in RAM, such as the processor can read these instructions from RAM and execute them in sequence. For example, we might have a program which reads some input into register 1, which is just a particular portion of memory within our processor. We can then have another instruction to add 5 to the value in that register, and then maybe we can write that value out to the monitor. That's a program. And so when we talk about creating a program, we're usually talking about formulating a series of instructions. Control units can't usually understand your instructions written in English, however, and so we write them in binary. This is just a number system consisting of ones and zeros, and we can encode information in this in various ways. For example, if we were to make our own processor, maybe we would define the binary sequence 0000 to be the add instruction, and maybe we would define the binary sequence 0001 to be the subtract instruction, and so on. Now, different processors may encode their instructions in different ways, and in fact may just have totally different sets of instructions which they can understand. This means that if we write a program in raw binary like this for one processor, we can't necessarily guarantee it's going to be able to execute on another processor. And actually remembering what series of binary digits relates to a particular instruction can be very tiresome anyway, so we have some abstractions over this to make writing programs easier. Wouldn't it be great, say, if instead of writing this binary on the right here, we could actually just write this text on the left and have it sort of translate to the binary on the right? In this case, we've just taken each instruction and given it sort of a textual representation so we can translate from the left to the right here on a roughly one-to-one basis. This is called assembly programming, and we say the assembly code on the left is assembled into the machine code on the right. Writing programs in assembly code is hugely more convenient than writing them in binary, but because our assembly language on the left is tied directly to a particular instruction set for a particular processor, we still have this problem that if we write assembly code for one processor, we can't necessarily guarantee it's going to be able to execute on another processor that uses a different instruction set or a different set of encodings for its instructions. Also, having to write every single instruction that you want the CPU to execute can get a little tiresome, so we have additional levels of abstraction on top of this. Wouldn't it be great, say, if instead of writing this binary on the right, we could write this much more abstract code which is much closer to English on the left, and then we could have this translated into the machine code. We could also design our more abstract language on the left so it's not dependent on a particular processor. So we could write this code on the left and compile it for my particular processor, and we could use the same code and compile it for your particular processor, and get different machine code binary output that works on both of our machines. If this code on the left is the C programming language, we say this text file gets compiled by a program called a compiler into machine code. So the process is that we write some text in a particular file, we then run that through a program called a compiler, which spits out some binary that can execute on a particular machine. If we then want to modify the behavior of the program, we can change our text file, we can change our C language code, then we can recompile our file and get a new binary output, and then we can run that binary if we want to execute our program. Within this model, most of computer programming then becomes about figuring out how to write this C code, which is the majority of what we're going to be doing in this course. So to get started, you're going to need to get yourself a C compiler, so you can write C code and compile it and run it and follow along. So you can use what's called an IDE, which is an integrated development environment, which essentially means you can write your code and run your code in the same place. Or you can use whatever text editor you like, such as Sublime Text or Notepad++, and then use a standalone compiler to compile your text file into a binary file. So in this series, I'm mostly going to be using Clang to compile, but occasionally I'm going to rely on Xcode for debugging and disassembling code, which are things we're going to talk about in future. So go ahead and set up a compiler on your machine so you can follow along. If you need a helping hand with this, there should be some notes to help you in the notes for this video, or if you're still having issues, there should be plenty of resources online which can help you out. So assuming you have a compiler set up correctly, let's test it out. If you're using some kind of IDE, just create a new C project, or otherwise just create a text file with a .c extension. Now let's actually test the compiler out, so I'm just going to type some text. I'm going to type the word test here and save the file, and let's see what happens if we try and compile this file. So I'm just going to compile with clang here, clang program.co program, and this is just saying to clang, hey, I want to compile the text file called program.c, and I want my output file to be called program. And we get some errors generated, so pretty much the compiler doesn't really know what to do here. So let's actually try pasting in some code that is valid C code. Now I've put a little bit of code into the video notes, so go ahead and copy and paste that into your C file, and let's try compiling it now. And this time you'll see we compile with no errors. Now don't worry about trying to understand this file because we're going to do that in the next video, but for now just know that this file compiles correctly, so it must be of correct syntax in the C programming language. Now actually, if I view the contents of my directory here, we can see that not only do we have the text file that I wrote, and by the way the text editor I'm using is Sublime Text, but you can use whatever text editor you like for using a standalone compiler. But I also see that we've got this file generated here called program, and this is actually the executable that the compiler has generated for us. Now, if I run this, so you can double click it, or you should know how to use your own operating system. Double clicking it is usually an option, or here I'm just going to run it from the terminal, and you'll see that, hey, actually nothing happened. It turns out this is a program that doesn't really do much, but it does compile properly, so you're really just testing your compiler at this point. Now, what I'm also going to show you, and don't worry too much about this, but I'm just going to paste this command into my OS X terminal, and actually you can see in the middle here all of these bits, all of these binary digits that the compiler has generated for us. And this is kind of the magic of programming at this level. We can see that actually we've just typed this little bit of text here, and the compiler's done all of the hard work for us and generated this file that our operating system can execute. And remember, the compiler really has done a lot of work here. It's had to read this kind of abstract code we've written here, which abides to some standard, and then it's had to spit out some binary that's going to work on my machine. It's had to output some specific machine code that's going to execute on my processor, such that my processor can read those bits from RAM and then execute the instructions to do, well, in this case to do nothing, but in future we're going to make it do more interesting things. So that's really all I have to say for this video. In the next one, we're actually going to go ahead and deconstruct this code that we've just kind of copy-pasted in here and we haven't really understood at this point. See you next time.